Right. So we are starting the session with a bit of revision of resolution of a vector into components. Okay, let's understand this concept. So supposing I have a vector which is like this. Right. It's a vector which is of magnitude, let us say 50, and with some particular axis. Okay, like this axis over here, and so with this kind of system of axes, suppose this particular vector is making an angle, like an angle of 30 degrees. Okay, and I specifically tell you that, okay, this is my x-axis, this is my y-axis. Okay, and it's given to me that the vector A lies in the xy plane as shown in the diagram. Okay, so resolve the vector into its components. That is, in other words, find the x component of the vector and find the y component of the vector, and then further, let us say we want to express the vector in terms of the unit vectors I cap and j cap. Okay, so can you just tell me over the chat how much ax and ay should be over here? How much should be ax, how much should be ay, and what will be the vector given in component form then? Yes, Adinath, Dhruv, yes, that is correct. No, Dhruv, you just mixed up the value. Cos 30 कितना होता है? Just to help you out, I'll tell you. Cos 30 is root 3 by 2, correct? And sin 30 is half. Yes. Devanshu, your answer is correct. For ax and ay, it is correct. Good. Dhruv, you probably mixed up sin and cos. Just check your answer. Okay. What about others? How much should be ax? How much should be ay? Just send me a note. Okay, so before we get into this question fully, okay, let me just revise the concept of components. So the general idea of components is, if a vector, yes, Dhruv, it is correct now. Okay, correct. Good. So if a particular vector has a magnitude A and makes an angle theta with the x-axis, okay, then to find its components, what we need to do is we need to drop a perpendicular onto the x-axis, and we need to drop a perpendicular onto the y-axis. And once we do that, then this perpendicular on the x-axis, which is like the base of this right angle triangle, that kind of thing, that becomes what we call the x component. Okay, and because it is along the x-axis, we write it as a component multiplied by a magnitude, multiplied by a unit vector, which is called I cap, right? So this is now ax I cap. This thing becomes ax I cap, whereas we draw this over here, this becomes ay j cap, where we understand that j cap is a unit vector, that means a vector of magnitude 1 along the y-axis. I cap is a unit vector, that means a vector of magnitude 1 along the x-axis. So this vector, the one which is along the y-axis, is of magnitude ay and pointing along the y-axis. This is of magnitude ax pointing along the x-axis. So then we express the vector a as the sum of the components ax I cap plus ay j cap. Now ax just becomes a cos theta. Yes, correct. True, that is correct, because here you're just using trigonometry. That if you draw this right angle triangle, so in this triangle, what is happening? This side is ay, this side is ax, and this hypotenuse is a, and this angle is theta. So as you can see, cos theta is base upon hypotenuse, and sine theta is perpendicular upon hypotenuse. So accordingly, from this we get this relation. Okay, and accordingly from this we get the relation that ay is a sine theta. So this is the general principle. Okay, so this is how we convert a given vector in terms of magnitude and angle into components. So given the magnitude of the vector and the angle theta, we can find the components ax and ay from these two formulae, formula 1 and formula 2. And the logic of those formulae are nothing but this trigonometric ratio, as all of you seen. Okay, so coming back to the above diagram, so you can see over here that when I drop this perpendicular on the x-axis, this component, which is ax I cap, so this ax will become 50 cos 30 degrees. So it will become 25 root 3. Okay, and I drop this. This will become ay j cap. So ay will become 50 sine 30 degrees. So it will become 25, and accordingly, so these are the components. Okay, so I've found out this. This is done, and now I want to express the vector in component form. So that will be nothing but 25 root 3 I cap plus 25 j cap, and in whatever unit that vector was, the components are in the same unit. Okay, so this is what we call the component algebra of vector, or expressing it in component form. Okay, so hope this is clear to all of you. Anybody has a doubt, any question? Okay, so now let's move on to one more example before we come back to Newton's laws, and we look at forces and how to apply this in case of forces. So why I want to do another example is because sometimes this might be given to us in slightly more complicated form. The way the question is given to us, or the way the diagram is made and we have to resolve, might be a little bit more complicated, like in this diagram I'm drawing next. Okay, so अभी मेरा XY axis ऐसा है, ठीक है, and in this, let us say I've got a force vector which is like this, is drawn like this, because a vector can be drawn anywhere, there's no problem with that. Okay, this angle is now 37 degrees, and the force is, let us say, 10 newtons. Okay, so the force F has a magnitude of 10 newtons. Okay, and lies in the XY plane. Now this is very important that it lies in the XY plane, because this force should not be pointing along an arrow such that it's kind of coming out of the screen. ऐसा नहीं होना चाहिए. It should be in the plane of the screen. because if it has a component which is coming out also, then it has what we call three components, x, y, and z. But here we are dealing only with two-dimensional vectors or two-dimensional components. So that means the arrow actually lies in the plane of the screen, or if you're drawing it on a sheet of paper, it lies on that sheet of paper, right? So it's like that. So anyway, so this force vector is of magnitude 10 newtons, lies in the xy plane as shown. So again, resolve it into components. Okay. Resolve the force into its components fx and fy and express it in component form. Okay. And express it in component form, or what we call I cap j cap form. Okay, here I will just again remind you of the trigonometric relations, that cos 37 degrees is 4 by 5 or 0.8, and sine 37 degrees is 3 by 5 or 0.6. Yeah, Bhomik, don't worry. We've just done one question before this, so I will send that across with the notes. Okay, just start with this. Okay, Bhomik, just start with this question. Don't worry about one more question we've done earlier. You can pick it up from the notes later. Anybody who's joined just now, don't worry. I'm recording the lecture, and you can just pick up just one question before this we've done. We can pick it up later. Now just concentrate on this particular question and tell me what the answer should be for fx and fy. Very good, Ibrahim. But only one thing here, you have to see also that the direction is like along positive x-axis or negative x-axis or like that, you know? Yeah, Bhomik, this is the question only. Okay, this whole thing is the question. What is there on your screen right now? This is the question. Yes, beta Bhomik, this is the diagram of the question and this is the language of the question here. That's all there is. Yeah, so Ibrahim and Devanshu, you got the values correct, but only one thing you have to see is it is pointing along positive x direction or negative x direction. Is it pointing along positive y direction or negative y direction? Okay, so the algebraic sign is also important. Yes, that's correct now. Good. Ibrahim, you got the correct answer. Adinath, your values are also correct, but algebraic sign is important, beta. अपन ना थोड़ा उल्टा हो गया है. Okay, the angle with the y-axis is 37 now. Okay, so see, in a case like this, in case of confusion, what you can always do is you can redraw your vector such that it starts from the origin. So let's look at this like this now. So if I draw the same above diagram, but such that, just to make things convenient for myself, I will now pick up that same vector from above. Okay, I'll pick up this vector, but instead of from here, I will draw it from here. So it will be a vector like this now. I'll draw it like this. So the same vector will come here. So when I do that, ये vector कैसा दिखेगा? It will be like this. Just a moment. Yeah. So in my xy plane, if I draw the vector starting from the origin, so that vector now looks like this. looks like this. It is of magnitude 10 newtons. Okay, and this angle is 37 degrees. Okay, so you can see that when I drop a perpendicular on each of the axes, okay, now here what should happen? This is 37, so this should be how much? Cos, but it's on the negative side. So this should be fy j cap, where fy you can see should become negative of 10 cos 37. So it should be minus of 10 into 4 by 5, or it should be minus 8. Okay. Whereas when you drop the perpendicular on the x-axis, you can see it's falling on the positive side. Okay. So you can see that this component fx will be positive. So यहाँ पे ये angle कितना हो गया? ये angle 53 है ना? So you can see that fx will be, you can write it as 10 sine 37, or you can also write it as 10 cos 53. Okay, and you can see that sine 37, which is 3 by 5, is the same thing as cos 53, just as cos 37, which is 4 by 5, is the same thing as sine 53. No, fy itself will be a negative quantity, beta. So the minus sign goes with fy in that sense. Okay, because I cap and j cap are standard unit vectors, no? So the difference between I cap and minus I cap, or j cap and minus j cap, is that this is opposite to this. Why? Because you multiplied it with a minus 1. So minus I cap is nothing but minus 1 multiplied by I cap. So this minus 1 makes it in the opposite direction. Similarly, if I write a vector minus 20 I cap, there's nothing but minus 20 as a scalar quantity multiplied with I cap. So the minus sign is showing you that it's opposite to I cap, and the magnitude is 20. Okay, understood, Yuvraj? Okay. So anyhow, so coming to this now, we will say that the components of the vector, so this is becoming how much? This is becoming 6. Okay. This is becoming 10 into 3 by 5. So that is 6. So the components are 6 newtons and minus 8 newtons. Okay, the y component will be negative because it is pointing along the negative direction, negative y axis. That's the point over here. No? Because if I said that no, the y component is 8 only instead of minus 8, then what difference this vector would have with respect to another vector which actually has a positive y component? You understanding my point, beta? अगर मैं fy plus 8 लिखता हूँ, so then that should be a vector like this, no? It should have a positive component. This would be a vector which has fx equal to 6 and fy equal to 8. But this one is like this. So it has fy equal to minus 8 newtons and fx equal to plus 6 newtons. And the force therefore in component form will be written as 6 I cap minus 8 j cap in newtons. Okay, so this becomes our final answer. Okay, Yuvraj, so hope this is clear to you, beta. Okay. So right now from this we will move on to application of this concept of resolved forces in Newton's laws. Okay. So let us move on to our next problem, which is now coming back to Newton's laws applications. Okay. So next up, let's come back to applications of Newton's second law. Okay. And as we have been discussing, in general, Newton's second law is that the net force on a body is equal to rate of change of momentum. Instead of calculus, we will use the language like this: delta p by delta t, where linear momentum is mass into velocity. However, for a body of fixed mass, okay, like any rigid body, what happens is mass being constant implies that rate of change of momentum becomes mass into rate of change of velocity, or it becomes mass into acceleration. Okay, so Newton's second law जिसका proper definition ये है ना, that net force is rate of change of momentum, but it becomes modified to a special form that net force is equal to mass into acceleration provided my mass is constant. Okay, so this is for mass being constant. And as we said that in this chapter, mostly we are always dealing with constant mass. Variable mass systems we are dealing in another chapter later, so we need not worry about this. So for us, Newton's second law is going to be this. Okay, so now let us look at application of this in certain questions. Okay, so let's come to an example where we have this situation. We have a mass of 10 kilograms, okay, which is lying on a frictionless surface. So this is lying on a smooth or frictionless surface. Okay. And acceleration due to gravity g pointing downwards is 10 meters per second square. Okay. Okay, Bhaumik, I will show you that part, don't worry. Now we are applying two forces on it. Okay. So two separate people are applying forces on it, F1 and let's say F2, like this. Okay. Yeah, Bhaumik, I'll show you, don't worry. So the body is initially at rest. Okay. At time t equal to 0, simultaneously two forces F1 and F2 such that F1's magnitude is 20 newtons, okay, and F1 is at 37 degrees with respect to the horizontal, okay, and F2's magnitude is 25 newtons, and F2 is at 53 degrees with respect to the vertical. Okay, start acting on the body continuously. Okay, so first of all, show all the forces acting on the body, okay, and resolve them. Okay, so resolve them into x and y components. Where x-axis is horizontal and y-axis is vertical. And secondly, calculate the body's acceleration. Okay, and third, normal reaction force from the floor onto the body. Okay, so just try this out. Yeah, Vomik, just take down this question and start working on it, and I'll take you through the section above. Though you've written that down before also. Right. So anybody got the answer? Have you resolved the forces first of all? Yes, Adinath, very good. The resolution is correct. Adinath, just check for F1, okay? The angle is 37 with the horizontal, no? So cos 37, remember, is 4 by 5 and sine 37 is 3 by 5. Remember this thing that cos 37 is 0.8 or 4 by 5 and sine 37 is 0.6 or 3 by 5. Yes, Aparna, it's correct. Okay. So just to give you a hint, your force F1 is looking like this. It's like this. It's of magnitude, how much is it? 20, and the angle with the horizontal is 37. No. So don't forget that it's this angle which is 37. This angle is 37. No. And similarly, your force F2 in the same diagram, if you draw F2, it would look like this. Its angle with the horizontal is 53 degrees. And its magnitude is 25. Normal reaction अपन ना, you're saying? नहीं, normal reaction weight से different होगा बेटा, no, because the vertical forces have to be balanced. Yeah, Adinath is correct now. Okay. So if you write these forces in component form, F1 is going to be 16 I cap minus 12 j cap, and F2 is going to be 20 I cap plus 15 j cap. Okay. So just use this resolution of vector that I've done on the side as a guideline of how to solve the problem. Now, keep in mind that we will also see the body accelerating in which direction. We'll see it accelerating along the horizontal direction. We won't see it jump up in the sky or something, right? It will be accelerating like this only. So whatever the acceleration is, it's along the x-axis. Okay. So Bhaumik, the cube will move along the ground. Na? The two forces F1 and F2, they have components which are parallel to the ground. One is like a pulling force, the other is the pushing force. So they will together, they will do what? They will make it slide along the ground, along my x-axis. Are you following now? No, it is not taking it above now because the weight is still dominating beta. Weight uska kitna hai? That's why I said that, first you resolve them and also show all the forces acting. Show all the forces acting. It's not just F1 and F2 now. There is mg also downwards. Don't forget that. And the ground is also pushing it upwards with normal reaction. So just imagine this situation practically, beta. There's a heavy block of 10 kg on the ground and you're applying a pulling force like F2, which is only 25 newtons. It will not come up on the ground. No? It will not come off the ground. It will slide only along the ground. You understanding why? Because the weight is very large. The weight is 100 newtons. उसको नीचे खींच रहा है weight. And that is pushing it against the floor. Right? So once you understood this resolution of forces, now let's come back to the actual block. Okay. So let's see what's happening to the actual block first of all. So coming back to the situation of the block, the block circumstances are now like this, that इस पे एक फोर्स F2 मैंने ऐसा लगाया, which was 25 newtons at an angle of 53 degrees with respect to the ground. Okay. दूसरा फोर्स मैंने लगाया F1. Okay. which is at 37 degrees with respect to the horizontal, okay, and which is of magnitude 20 newtons. But apart from this, the block also has that giant force of gravity acting on it. It has mg, which is acting vertically downwards on it, and that is 10 newtons. Sorry, that's 100 newtons, my mistake. M itself is 10 kg. So this is 100 because the mass m is 10 kilograms. And the floor is pushing it up with yet another force, which is the normal contact force. And that is the normal reaction which we have to calculate. Okay. So there is a combination of all these forces. Understanding? Now on this we have to apply the equation that net force is equal to mass into acceleration. Okay. But because the forces are acting in various directions, we will resolve this. We will divide this into components. Okay. Where we'll say x axis is the horizontal axis. We will take our system of x and y axis like this, that the horizontal direction is our x axis, the vertical direction is our y axis. So our system of x and y is like this. So along the horizontal direction, is our vertical axis. Now, when we are solving this, what we will see is that the acceleration of the body is going to be horizontal, is going to be sliding along the floor. So the body is sliding like this. So this acceleration here is along x-axis, which also means that along y-axis there's no acceleration. So along horizontal acceleration, what is happening? There is an acceleration of magnitude a, whereas along the vertical there is no acceleration. Okay, understood this, people? Okay. So next thing we will understand therefore is that the net horizontal force, that is summation of all horizontal forces, should be equal to m into a, whereas summation of all vertical forces should be 0. Okay. In other words, the vertical forces should balance. Because there's no vertical motion. Whereas the horizontal forces, the net horizontal force is equal to mass into acceleration. Okay. So are the steps clear up to this point, people? Just a minute, I'm resharing the screen. Okay. So now next thing what we need to do is we need to find out this equation separately. And we need to find out this equation separately. So for this, what we have to do is resolve the forces F1 and F2 into horizontal and vertical components. That's the next step. Okay, so that we have already done above. You can see that we have done this somewhere. I can find it. Yeah, we've done this already here. Okay, so using this, you can see that I've already done this. F1 was 16 I cap minus 12 j cap, and F2 was 20 I cap plus 15 j cap. All right. So what I'll do next is in the free body diagram above, or in the diagram of forces above, we will replace F1 and F2 with the equivalent components. So what we'll show is that this force F1, इसका horizontal component कितना है? It is 16. और इसका vertically downward component कितना है? It is 12. And this force F2, its horizontal component is how much? It's 20, but its vertically upward component is how much? 15. Okay. So now it is like on the same block, it's like this force F2 that we had, it has a horizontal component, X component, which is of 20, and it has a vertical component upward, which is of 15. All right. This other force F1, it has a horizontal component of 16, and it has a vertical component which is downwards, which is 12 in magnitude. Okay. It's minus 12. So the direction is downward, you can see. Okay. And apart from this, there is mg, which is 100 newtons. Okay. And there is a normal reaction which we don't know. So there is some, beg your pardon, upward normal reaction. Okay. And all these forces together are giving the horizontal acceleration of E. All right. Where this is our x-axis and this is our y-axis. Okay. So this is the forces in resolved form. Okay. This diagram is showing all forces in resolved form. Whereas the above diagram was showing us just the forces without the resolution. Okay. So just understand the relationship between this diagram and the above diagram once. Then we can proceed with more about the question. Just a moment. Yeah, so understand the correlation between these two diagrams. Okay, so hope all of you are following up to this point. So all I've done is, in the above diagram we had the forces with their directions 53 degrees and 37. अभी F2 को मैंने components में break कर दिया, horizontal component, vertical component. F1 को मैंने component में break कर दिया, horizontal component along the positive x direction, vertical component along the negative y direction. Now once I've done this, next I'm going to do what? I'm going to invoke these equations. Now, this equation 1 here and this equation 2, I'm going to solve these. Solve equation 1 and 2 using this diagram. All right, Bhaumik, what happened, beta? You're not getting the video properly. Okay, so anybody got the answer? Yes, Bhagyashri. Very good. Aparna, correct. Normal reaction is correct. And what about the acceleration, beta? Okay, no problem, Bhaumik. I will send you the recording today itself. Don't worry. Yes, Aparna, your normal reaction is correct. Acceleration is also correct. Good. What about others? Ibrahim, Adinath. Yeah, Adinath, correct. Bhagyashri, correct. Yes, Dhruv, correct. Yes, Adinath, your acceleration is correct. Yes, Adinath, correct. Okay. Ibrahim, have you worked out the question, beta? Okay, okay, no problem. Okay, so here now let us apply the concept that along x-axis, what should happen? Net force, that is summation of all forces along x-axis, should be equal to mass into acceleration. So summation of forces along x-axis is what? F1's x component plus F2's x component. There's no other force along the x-axis. That should be equal to mass into acceleration. So magnitude wise, these are 16 and 20, and that should be equal to 10A, where these are in newtons and this side is in kilogram. So the acceleration will come out to be in meters per second square. So the acceleration, as you can see, will come out to be 3.6 meters per second square. Or if we write the acceleration in vector form, we will write it as 3.6 I cap meters per second square. Yes, very good. That's correct, beta. Okay. Now, whereas along the vertical, along y-axis, our net force, that is summation Fy, should be 0 because there is no vertical motion. And the block is sliding along the horizontal ground. So that means now you see our vertical forces, n is coming with a plus sign because it's along the positive y-axis. F2's y component is coming with a positive sign. Okay, but mg is downwards, and F1's x y component is also downwards, and this should be 0. That means the sum of normal reaction plus F2's y component should balance the sum of weight plus F1's y component. No. So this is showing that the upward forces balance the downward forces. Upward forces balance the downward forces. So what this is telling us now next is that n plus 15 should be equal to 100 plus 12. So that is telling me that the normal reaction is 97 newtons. Okay, and obviously it's upwards. The direction of the normal reaction is upwards. So this is the final solution of this. Understood, beta. So these are the steps that we have to do when we have a problem where there are forces acting in various different directions. If the forces are acting in such directions that they are diagonal, some of the forces are neither horizontal nor vertical, then we have to divide the force into components, horizontal components and vertical components, and accordingly we have to calculate. So that's what we did. We started by understanding that, okay, in this body I'm applying two external forces like this, but apart from that there are also two other forces. There is gravitational force and it's in contact with a horizontal surface, so there's a vertically upward normal reaction. So मुझे पता है कि including F1 and F2 there are four forces acting on in all. So first of all I understand this diagram, that what are all the forces acting on the body. They are these four, which we have understood in this diagram. Next I see that, okay, out of the four forces, two of them are okay, they are vertical, but the other two are having components, both horizontal and vertical. So I come to my next step, which is called the resolution of the forces. We resolve the force vectors into their x components, that is horizontal and vertical components. So that is where your vector algebra comes in. Now, because this angle is 53, so ये component F2 cos 53 था, ये component F2 sin 53 था. So like that we resolve the forces. And next what we do is we show all the forces acting on the body, but now in resolved form, such that they are in terms of their components, their x and y components. So that is this diagram now. And once you've got that, separately now we see what is happening along the x-axis. Along the x-axis, the net force is equal to mass into acceleration. And along the y-axis, what is happening? The net force is 0 because the forces must be balancing each other. Why? Because we know that the body is moving only horizontally. It does not have any vertical motion. Okay, so just leaving you with a moment here to note down this part here. This will finally give us normal reaction as 97 newtons, which I've shown below. But okay, so just take this down and understand this thoroughly. Please ask me if there's any doubt, and then we'll move on to the next question. Okay, people. So hope this question is clear. Now let's move on to another example. So our next example, we have two blocks which are in contact. Okay. So they are on a frictionless horizontal surface. And now what we are doing is we are pushing the combination with a force like this, such that, okay, so given that m1 is equal to 6 kilograms, m2 is equal to 4 kilograms, take acceleration due to gravity as 10 meters per second square. Now an external force F of magnitude, okay, 5 newtons, okay, is applied at 37 degrees to the horizontal on M1 as shown. Okay. So what we have to do next is find the acceleration of the blocks. Okay. Find the normal reaction force between M1 and M2. That is, they are in contact. M1 and M2 are in contact with each other. So there is a normal contact force between them. So we have to find that one. And we have to also find the normal reactions on M1 and M2 due to the floor. How much normal reaction the floor is applying on each of these blocks. So just try this out, people. Yeah, anybody got the answer, people, for acceleration? Yeah, Bhageshi, correct? Yes, Aparna, correct. Ibrahim, correct. Good. Aparna, beta, you made some mistake. Just check your numerical value. Yes, Bhageshri, correct. Adinath, correct. Okay. So let's understand, when you're pushing this block from this side, it starts accelerating, and because it's pushing this one also accelerates. So they will have a common magnitude of acceleration and common direction of acceleration. दोनों का acceleration same होगा. Okay. So if you look individually on the blocks, how forces are acting, you'll realize that individually on these blocks, let's say this one is M1. Okay, it's not that they're not in contact, but I'm just drawing them separately so that we separately understand the forces acting on them. Okay, so on M1 we are applying this force, okay, which is 5 newtons at an angle of 37 to the horizontal. Okay. Apart from that, it has its own weight, M1g. Okay. Now this block pushes this block with some kind of normal reaction. Okay. So by Newton's third law, this will push this back with an equal and opposite normal reaction, like this. Okay. And of course, the ground will be pushing this up with some force. So this is normal reaction due to the ground. This block M2 has its own weight. Okay. And of course, the ground is pushing it up. with some normal reaction N2. Okay. Now, at the same time, we can see that both the blocks are accelerating along the horizontal direction with a common value of, or with a common magnitude of acceleration. So in terms of resolution, what we should do here is, again, we should take our x-axis as a horizontal axis, and our y-axis as a vertical axis, and we should resolve the forces. Right. So for the block M1, now we'll just do it in brief. We can see that this force F, it will have an x component of F cos 37 and a y component of minus F sin 37. So this force will have an x component which is 4 and a y component which is minus 3. So when I show it in resolved form over here, this will show an x component of 4 and a y component of 3. Okay. Then of course there is the weight, which will be 60 newtons, right? And there will be some normal reaction which we have to calculate. Okay. And there is some normal reaction that the other block is applying, which is backward, which also we have to calculate. And the combination of these forces is giving it an acceleration E. So this becomes the situation in terms of resolved forces, for this block M1. Similarly, the situation for the block M2 somewhat simpler, because only the normal reaction by which M1 is pushing it is giving it horizontal acceleration. So इस पे एक ही horizontal force है. Now this and this are an action reaction pair. So keep in mind, these are an action reaction pair. So they are equal and opposite. Okay. So apart from this, there is the weight of this guy, which is 40 newtons. And there's some normal reaction that the floor is applying on it. And this is also having the same acceleration, E. Okay, so this is now, we have converted this into resolved forces. This is the original forces which are acting. Now these are the resolved forces. Okay, where of course we understood at the beginning itself that M1 was 6 kilograms and M2 was 4 kilograms. Now let us write the equations. Now let's write Newton's second law for block M1. So along the horizontal, what is happening? The net force should be equal to M1 into acceleration. So what are the net forces which are acting along the horizontal? It is Fx minus N. So that is nothing but 4 newtons minus some normal reaction is 6e. So let us say this is what we are writing as our equation 1. Okay. Now for the vertical direction, summation Fy should be 0. It should be balanced. So what are the vertical forces acting on this block? We can see there is plus N1, okay, minus F's y component minus M1g is 0. That means this normal reaction is balancing the sum of the weight plus the vertically downward component. So this normal reaction N1 is 60 plus 3 or 63 newtons. This is our second equation, which is directly giving us a result. The first equation didn't give us a result directly because there were two unknowns in it, N and A. Okay, so this is our second equation. That's done. So this was for block M1. Now similarly, let's apply Newton's second law for block M2. Okay, so the horizontal one, summation fx should be equal to mass into acceleration. So this will give us n is equal to, this one's mass is 4 into acceleration e. So this is becoming our third equation. Okay, and along the vertical, forces should balance. So it's very simple. So N2 has to balance the weight. So N2 is directly becoming 40 newtons. So this was our fourth equation. We had four unknowns, N1, N2, N, and E. We had four unknowns, so we needed four equations. Now we are done. Okay. So now solving equation 1 and 3. So now from this you can see equation 1 is 4 minus n is equal to 6a, and equation 3 is that n is equal to 4a. So we just add these two equations. You get 4 is equal to 6 plus 4e. So that tells you that the acceleration is 0.4 meters per second square. Okay. And it also tells us that the normal reaction between the blocks is 4 into a, so 4 into 0.4, so 1.6 newtons. Okay. So that's the acceleration. This is the contact force between the blocks. Okay, and these two are the normal reactions applied by the floor. Okay, this and this are the normal reactions by the floor. All right, so I'll just leave you with a moment to analyze this. But the process is the same as we had done in the previous question. Only difference is now we are having to apply it to two separate bodies. Now they are moving together, but we are going to have to apply it to two separate bodies, wherein they are in contact with each other. So they apply a contact force on each other. And that contact force ensures that M1 is pushing M2 and making it slide along with it. So the two objects are moving in combination. Just excuse me for a moment. Yeah. So the first part is this, that you convert the actual forces into resolved forces. So only F3, F was the diagonal force. So you broke it into horizontal and vertical component. Yes, Ibrahim, very good. You got the answers correct. Adinath, correct. Yes. Aparna, I think you made some mistake in calculation. Is it clear now, beta? Okay. Okay, so anyone having any doubt with the solving of the equations? Okay, so this is just simultaneous equation solving. That should be pretty simple. Okay, now let's move on to the next aspect of Newton's laws, where we'll now look at the type of forces that act in threads or strings, okay, or ropes, or chains, those kind of materials when they are stressed, because they are being pulled or they are being extended. So that type of force, as you know, is called tension. So the next type of force we will see is tension. Okay, acting along a rope or thread, okay, or chain, okay, when it is given a tendency to stretch, okay, due to external forces. So the thing to understand is that tension always acts along the length of the thread, chain, or rope, or whatever. Okay. And secondly, if the thread, rope, or chain is massless. Now, of course, nothing is perfectly massless. It means that it's of negligible mass. That means extremely small mass. Okay. Then the tension is always uniform at all points. Okay. So let us understand this whole concept with an example or two. But first, you can just make a quick note of these 2 points. So these are the two important things to understand about tension. Okay. That the direction of the tensile force or tension is always along the length of the thread or chain or the rope. And secondly, that as long as the mass of the chain or the rope or the thread, whatever I'm considering, is very small, it's negligible compared to the other masses in my system, I can treat the tension as a uniform force. Tuko. Okay, so as I said, we'll understand these 2 points better as we look at actual physical examples. So the simplest way of understanding tension, let's start with that. So suppose we have this situation. Okay. This is a wall and there's a floor, and we have a kind of heavy rope. Okay. But it's kind of lying on the floor. or it need not be heavy also, but it's just a thick kind of rope. So this is a rope, okay, which is attached to the wall at the end A, okay, but it is lying loose on the floor. So in that case, what happens? The tension T is 0. There is no tensile force along it. Okay. But now, in the same situation now, if I do this, if I engage an external agent to start pulling the end B of the rope, so now what is happening? The end A is attached to the wall over here like this with something like a hook. But what I'm also doing is, now this other end B, I'm pulling it with an external force. So somebody or something is actually pulling this side with some external force. Let's say 10 newtons. So what we observe now in this situation is that immediately on application of the external force, okay, the rope becomes what we call taut, or it becomes tight, or it becomes kind of stretched out, okay, and as a result of that it develops, okay, and it develops a tension T, which is a force along its length. Okay, so we'll talk more about this. First, note down this diagram. I'll explain. Hey, why are you holding? Hmm? Okay, so let's understand what's exactly going on over here. So look at the situation of the rope, and remember, forget about its mass. You know, its mass is negligible. Okay, so that's a given. We've understood before that the mass is negligible. So its mass is tending to 0. So don't worry about the weight. Whatever small weight of few micrograms or whatever there is, it's being balanced by the floor. So we don't need to worry about that as a force. But what is happening is that the moment we are pulling it with a force F from this side, okay, the moment we are pulling with a force from this side, the hook on the other side will also apply some reactionary kind of force. So there's a reaction force that develops between the hook at the end A. And that pulls it back. And that is why the acceleration is 0. So basically that reaction force, the net force is 0. So that reaction force is exactly equal to the external force we are applying. And that's equal to 10 newtons. Okay. But as a result of that, the string develops an internal force which we call tension. And that force looks like this. So that force acts on, for example, if a person is pulling the string at the end B, so that person's hand will experience an equal and opposite force because of the rope. So if there's a person here who's pulling on the rope with a force F, so the person's hand experiences an equal and opposite force, which is the tension. So T is equal to F. And on the other side, the hook is applying a force of R on the chain or on the rope. So the hook itself on the wall, that experiences an equal and opposite force of tension, like this. So this T is equal to R. So T is equal to F, which is equal to R. So this T is the tension force that develops along the length of the string or the rope. Okay, because it is stretched out now, stretched by the external forces F from one side and the reactionary force from the wall on the other side. These two forces they're pulling it apart like this. So as a result, that string is developing a stiffness, or it's becoming taut, the opposite of relaxed, and is developing this kind of force along its length, which we call tension. So this is a very natural example to understand the property of tension. Now, the moment we have applied forces externally in such a way that we are giving the string a tendency to get stretched out, it develops this property of force or this property of tension along its length. Just bear with me a second, guys. I'll get this correct. Okay. So this is what happens over here. So initially, when we are not applying any force, the string was in what we call a relaxed condition. But the moment we give it this tendency to get stretched out by the application of this external force, this is what happens. It develops a uniform tension throughout its length, which is equal to the amount of external force we are applying F. Okay, people. So hope you are clear about this situation. Okay. Now another very easy situation to understand how a string can develop tension is if we use it to vertically suspend some weight. So next situation we'll see something like this. Now from a ceiling, okay, there's some kind of a hook, and now there is a light rope, a light string, which is just kind of hanging. Okay, so this is a thread or a string of mass tending to zero. So in this case, what will happen is kind of loose. Okay, so there is no tension in the thread. Okay, but if I use the same thread now to suspend some mass, this diagram is in a vertical plane, so gravity is acting downwards. Okay, so the moment I do this, I attach a block below or something, you will see that it gets stretched out. Okay, so if I have suspended some weight using some hook over here, okay, so because of gravity acting, now what happens is that the string becomes stretched. The thread or the string is now taut, okay, or it is stretched out, okay, and it has a tension. So it develops tension T. Now that tension acts along its length. So you can see that on the block, what is happening? There are two forces acting. One is vertically the tension that the thread is applying on it and its weight. So the tension balances the weight. The weight of the block. Okay. Whereas if you look at the ceiling, the hook on the ceiling, that will now experience a downward force which is equal to the tension. So the tension will become equal to mg. Yes, that is correct. Yes, Dhruv, the tension will become equal to mg. Okay. So suppose the mass of the block is 10 kgs, the tension in the string will become equal to 100 newtons. Okay. So the heavier the block, the more the tension in the string. Okay. So the thread or string develops tension T such that T is equal to mg. The magnitude of the tension is equal to the weight of the block. Okay, so understood this example, people. This is another situation of, how external force acting on the string, giving it a tendency to get stretched out, creates this situation that it goes from a situation of being loose to a situation of becoming what we call taut or stretched out. It develops tension. Okay, so let's look at an example, a numerical example with this kind of application next. So I'm sure this is clear to all of you. Okay. So our next example is now like this. Okay. So we have this situation now. Okay, so we have a combination of two blocks. And a combination of two threads. This one is A and this one is, okay. So both threads are extremely light. That is, their mass is very small, tending to zero. Okay. So given that the blocks are of mass 5 kilograms and 15 kilograms, okay, and G is equal to 10 meters per second square, we have to calculate the tensions in the threads E and B. Okay, just work this out, people. Should be fairly easy. Yes, Dhruv, that is correct. Yes, Aparna, correct. Yes, Adinath, correct. Yes, Bhageshi, correct. Yes, Yuvraj, correct. Okay, so first of all, we'll have to understand that the thread A will apply a tension, let's say TA like this on the hook. Yes, Ibrahim, correct. Very good. A tension like this on this hook. And similarly from below here, it will apply a tension TB like this on this and a tension TB like this on this. Okay. So now given this situation, if we look at the forces which are acting on the block M1, for example, and the forces which are acting on the block M2, for example, just from the above diagram, you can see on M1 and M2. I'm just showing them side by side, even though they are actually placed like this. So on M1, there is an upward force of TA. There is a downward force of tension on this, and there is its own weight. Okay, and it's in equilibrium. Its acceleration is 0. Similarly, on M2, there is a downward force of its own weight, and there is the upward force of tension in this, and its acceleration is 0. Okay, so you can see that now balancing the forces for M1, we have the equation that TA, the upward force, has to balance the sum of the two downward forces, that is weight plus TB. Block M2, we have the equation that the upward force TB has to balance the downward force. This. So from equation 2, you can see that tension in this string is 150 newtons. Okay. Now substitute this in equation 1 and you will get TA is equal to, how much is this now, 50 plus 150, so that's 200 newtons. It's very simple, nothing very confusing in this. So okay, now the entire part is there, Bhumik. I've not written anything else. Yuvraj, to answer your question, a spring is a slightly different situation compared to a thread or a rope. A spring actually stretches in length, whereas a rope or a thread does not really stretch in length. It has a tendency to stretch, but its length remains the same. Okay, is it clear, Yuvraj? So it is like, the more the amount of mass. So if I replace the thread with a spring, so what will happen is that if the spring had a natural length, which was L. That is, when no mass was attached, its length was L. Now, under the action of the mass, it stretches by X. So what happens is that the extension of the spring, the length by which it elongates, you can also call it the elongation. That elongation becomes proportional to the weight of the block. So the larger the weight of the block, the more the spring gets elongated. And yes, obviously every material has a breaking stress. So if the elongation has a tendency to become more than a certain limit, then instead of the spring being able to bear the weight, it will actually break at some point. That can happen to a thread also, or a rope also. So there's a maximum tension that the thread or the rope or even the spring can withstand, and that is called the breaking strength. Okay, beta Yuvraj, does that clear your point? Okay, let's move on to another example. Okay, good. Okay, let's move on to our next example. Now here we'll have to come back to resolution of forces. So this time what is happening is that we have an inclined plane like this, with a kind of wall at the top. Okay. Okay. So anyway, so this inclined plane is at an angle of 30 degrees to the horizontal, and it's a smooth surface. So it's a smooth inclined plane. Gravity is vertical and equal to 10 meters per second square. Okay. Now there is an object here, like a block or something. This is of mass m, and again there is a light thread which is keeping it from sliding down. So we have to find the tension in the thread, given that we know the mass of the block. Okay, so this is light thread. So given that the mass of the block is 20 kg, first of all, show all forces acting on the block. Okay. And then calculate the tension in the thread, and also calculate the normal reaction between the block and the inclined plane. Okay, so just work this out, people. This will again be an exercise in resolving the forces for you people. Okay. So take your time easily and understand how to resolve the forces and work this out. Yeah, that's correct, Ibrahim. Normal reaction is correct and tension is correct. Okay. So when we look at this block, okay, if we look at the forces acting on it, there is a normal reaction force that the floor or the inclined plane applies, which is in this sort of direction. It has to be perpendicular to the surface. So this has to be along this 90-degree line. Okay. Then there has to be a tension that the thread applies. I mean, why show it like this? So the tension that the thread applies is directly along the thread. So it's a force like this. Okay. And of course, there's gravitational force acting on the block because of Earth, and that is acting vertically downwards. mg. Now all these together are keeping the block's acceleration 0. So the net force on the block should be 0. So that means when we resolve the forces, the net force along x-axis should also be 0. The net force along y-axis should also be 0. No, Aditya, normal reaction will not be equal to weight over here, because you can see now their directions are different. Okay. So let's understand this diagram in a little bit more detail. Okay. So if we represent the block by a point mass, so we'll understand what are the forces acting on it. There is mg, which I've already shown, acting vertically downwards. Okay. There is normal reaction, which is not acting vertically upwards now. It is acting like this. So this is going to be key to our analysis, to understand what is the direction of normal reaction. And there is tension is acting because of the rope, which is along this direction. Now the rope or the thread is, remember, parallel to the inclined plane. So this is the direction of the inclined plane. Okay. Whereas if this is the horizontal, you can see this angle here is 30 degrees, correct? This angle. Okay. And similarly, if you look at the direction which is perpendicular to this angle is 90 degrees. Okay. So that means that again, this angle will be 30 degrees. Okay. You understand now, because the tension acts along the thread, which is parallel to the inclined surface. Okay. Whereas normal reaction acts perpendicular to the surface. Okay. And weight acts vertically downwards. Okay. Now, so the next question becomes, how do we resolve the forces? Okay. So for resolving the forces, we have two options. One is that, okay, for resolving, one option is that we can take our x and y axis like we normally do, like take it horizontal and vertical. But that is not the good option actually here. This is an option which we will not take. Okay. I'll show you why this also. But another option is we can take our x-axis along the inclined plane. And we can take our y-axis perpendicular to the inclined plane. We can do like this also. So this angle is 30 degrees. Okay. What is the advantage in doing this? Then only one force has to be resolved. mg has to be resolved. The other two forces don't have to be resolved. So directly the tension is acting like this. Okay. Directly the normal reaction is acting like this, and only mg has to be resolved. So mg, which is acting vertically downwards, where this angle is 30 degrees, this is the only force which now has to be resolved. Okay. Okay. So we'll resolve mg now. Instead of resolving the other two, we'll resolve mg in this method. and this component of mg will become mg cos 30, and this component of mg will become mg sin 30. So we've resolved this. Okay, so that is why this is the easier method rather than this method, because only one force has to be resolved, mg. ऐसे करेंगे तो we have to resolve two of the forces. Okay, so if we go by this now, because the object is in equilibrium, the net force along the x-axis has to be 0 and the net force along the y-axis has to be 0. So mg we've already resolved, no? So remove it from our analysis. Okay, so okay, so having removed mg from the analysis and replaced it with the components, we can see that summation fx is 0. That means what is happening? Tension is balancing mg sin 30. That becomes our equation 1. And along the y-axis, net force is 0, because the acceleration of the block is 0. Okay. So that shows us that normal reaction is balancing mg cos 30. Okay. So that shows us that the tension will equal 100 newtons and normal reaction will equal 100 root 3 newtons. Okay. We could have also gone with this, but here we would have had to resolve two of the forces. So that's the reason why we avoided this. Now, if we went with this, there's no problem. We can still do this. Tension is acting like this. Okay. Normal reaction is acting like this. Okay. And mg is acting vertically downwards like this. But now the thing is that it would be a little bit more tedious, because we would have to resolve two of the forces. So we'll have to take tension's x component as t cos 30 and tension's y component as t sin 30. Okay. And then take similarly normal reactions y component, that would become n sin 60, because this angle is 60, and normal reactions x component, which would be along the negative direction but would have a magnitude of n cos 60. Okay, and then here summation fx is 0, means we would write that nx balances tx. That means n cos 60 balances t cos 30, and summation fy is 0, means that n's y component plus tension's y component balances mg. Okay, so in other words, this becomes n sin 60 plus t sin 30 is equal to mg. So this would be our first equation, this would be our second equation. So our first equation would be like this, that n cos, so n by 2 would be equal to root 3 by 2 t. And our second equation, okay, and our second equation would be this. Okay, and then we would substitute this over here, and substituting that would give us this result. Okay, so that is how you can see that it's actually disadvantageous to take the x and y axis as vertical and horizontal. You are having to put more effort in solving the problem. It would be more advantageous to take the x and y axis like I've taken there, which is along the sorry, along the inclined plane and perpendicular to the inclined plane. Just give me a moment. I will I'll resolve the whiteboard such that you can see both the cases clearly. Okay, so the actual forces acting on the body are tension, normal reaction, and weight, and their sum should be zero, because the acceleration of the body is zero. So net force should be zero. So to make net force zero, we have to resolve. Now these are the two systems of resolution I'm showing. One where we have taken the x-axis along the inclined plane and the y-axis perpendicular to the inclined plane. And this is the easier of the two because then I'm having to resolve only mg. Whereas this is one where I've taken x-axis horizontal and y-axis vertical. But here I'm having to put more effort because I'm having to resolve both the normal reaction into ny and nx and the tension into tx and ty. So the preferred method becomes this one. This becomes preferred over this because this is more lengthy. Both will give you the same result, of course. Both will give you the correct result. But this is the final way of solving. Okay. So people, with that, we come to a conclusion for today's lecture. Okay. Now, last time I had also listed out some questions for you to do from your module. So hope you are doing those questions, and at some stage in the next couple of lectures, we will discuss those questions also. Okay. So you've done the questions, very good. So if there are any doubts while solving the questions, you can send me doubts. I will give you some hints over WhatsApp. Okay. So thanks for attending, people, and that's it for today. I will send you the recording as well as the notes in PDF form. Okay, and all the best and stay safe, all of you. That's it, guys.